So finally, let's see an example of how we can solve these tricky expected value problems using linearity of expectation. So let me give kind of an overview of how the strategy works, and then we'll do an example. So this sort of form of problem that we usually are able to attack with linearity of expectation is find the number of times something happens and the situation is that it's hard to find the number of times it happens sort of for general outcomes. But it's easy to find the probability that it happens in a particular case. And often, so the idea with linearity of expectation is that you can break the problem down into these simpler cases. And often, the way you break it down is by defining a sort of indicator variable. So what I mean by this is you define, for your purposes in this problem, a new random variable, xi, or x, whatever. It'll depend on the application that you're using it for. But you define a random variable that is 1 if the thing happens in case I, and 0 if it does not. And then the point is, when you take the sum of these indicator variables xi, basically you're taking a 1 in this sum for each time the thing happens. That means when you add it all up, you'll get the number of times it happens total. So to find the expectation of this side, you just need to be able to find the expectation of this thing, which amounts to finding the probability that it happens in that particular case. So hopefully that made some kind of sense, but I think it will make much more sense when we do it concretely in an example. So let's do this example. Flip a fair coin 10 times. What is the expected number of initial heads in this sequence of flips? So this means how long is the run of heads at the front if there is one at all. So for example, if you start with the tails, then you get a 0. There are 0 initial heads. If you get heads, tails, then there is 1 because you have a run of 1 head at the start. If you have something like heads, 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 tails, heads, tails, heads, this gives you 3 because it has 3 heads at the start, and so on. So in 10 coin flips, what is the expected number of heads at the start of the sequence? Number of initial heads. And this fits into our framework because finding for a general outcome, sort of like computing for general outcomes, how many have certain numbers of initial heads is a little bit tricky, but we can break it down into these indicator variables like so. So define for I equals 1 up to 10, xi is 1 if first I flips are all heads and 0 otherwise. Excuse me. So the idea is, for example, if we have a sequence like this, then basically let's look at what our variables we've defined are. So x1 is 1 if the first flip is heads. So x1 is equal to 1. x2 is equal to 1 if the first two flips are both heads. So that is a 1 as well. x3 is a 1 if the first three flips are all heads. So we get a 1 there. x4 is 1 if the first four flips are all heads. Now this is not the case. Fourth flip is a tails. So we get a 0 for this guy. And then since we're considering all of the first that many flips being heads, basically as soon as we get a tails, they're all going to be 0. So hopefully that illustrates that what these are doing is they're exactly measuring the number of initial heads, right? We get 1s for each initial head and then 0s afterwards. So the idea is that the sum of these indicator variables, xi, from I equals 1 to 10, will equal the number of initial heads, which is exactly the thing that we are trying to calculate the expectation of. And this is easier to calculate the expectation of because it's a fixed number of flips and it's a fixed outcome of that number of flips. So the probability that xi equals 1 is, what is the probability that you flip a coin I times and get heads every time? That's just 1/2 to the I. Because, well, you can think of that in a binomial distribution type way if you want, but you can also just think of it as a product rule, because we're prescribing the outcome for every single coin flip. So we just need to take 1/2 to that power. So the expectation of this variable is 1/2 to the I times 1 plus whatever the probability of 0 is, which is just like, let's write it anyway, why not? It's 1 minus that. But it's times 0, so this term is going to go away anyway. And this is just 1/2 to the I. So by linearity of expectation, we have the expected number of heads, expected number of initial heads, is the sum from I equals 1 to 10 of the expected value of xi, which is the sum from I equals 1 to 10 of 1/2 to the I. And at this point, this is something that you can just compute out. Maybe it's going to take more than just a couple seconds, so maybe I won't do that right now, but it would be easy enough to figure out this exact value if you wanted to. But just from eyeballing it, it looks like it's going to be close to 2. It's going to be right about 2. So this is the basic idea of using linearity of expectation. Let me give not a full example, but just one more example of how to sort of figure out what these indicator variables are supposed to be doing. So there was a problem, I believe, on the practice exam, which is roll 10 dice. What is the expected number of pairs that add to 7? So our indicator variables should be, we define an indicator variable for each pair, which is 1 if it adds to 7, and 0 otherwise. And then when we take the sum over all these indicator variables, that will give us a 1 for every pair that adds to 7, and they will add up to the number of pairs that add to 7. And we'll be able to use precisely the same strategy with linearity of expectation to find that expected value. You can find more on that in the solutions.